The use of poisons in war, specifically poison gas, started in the First World War. But one of the most potent poison gases, nerve gases, ever discovered is the compound called sarin. And this was developed by the Germans in the 1930s and taken over by the German military. And in the World War II, the Germans stockpiled a lot of sarin, but it was never used. And most of it was discovered by the Russians as they pushed through into Germany. All sorts of countries have made and have stockpiled sarin. And most quite recently, we've seen that the United States going to the verge of military action against Syria because of the use of sarin in the Syrian civil war. One terrible use of sarin was back in 1988, when the Saddam Hussein's military in Iraq used it against villagers up in Kurdistan in the north of the country. Sarin is a very, very powerful nerve agent. It gets into the body, it stops the nervous system working, and even with very low doses causes death. It's not just governments that have made sarin. This cult, this Japanese cult called Aum Shinrikyo, also had a go at making sarin. And they released some in a town called Matsumoto in June of 1994, killing 7 people. The following year, they carried out the well-known Tokyo subway attack, where they released their homemade sarin in the Tokyo subway. They killed 12 people. 1,000 people at least went to hospital. And even today, there are still people suffering the ill effects of that attack. Fortunately, the Aum Shinrikyo chemists weren't very good at their job. The sarin they produced wasn't very pure, and it smelled very badly. If they'd made pure sarin, then the death toll would have been much, much higher. Well, how do these nerve agents work? They work by interfering with the biochemical mechanism in which nerve impulses travel from the brain to the muscles. So this is a nerve cell, and it does look like a piece of wire, and in some ways it acts like a piece of wire in transmitting the message. So how does a nerve cell actually work in chemical terms? Well, let's consider a nerve cell in its resting state, where nothing is going on. Here's the nerve cell. Before it is the previous nerve cell. In front of it is another nerve cell. And it's this line of nerve cells which will ultimately carry the impulse from the brain to the muscle. Well, at the resting state, there's potassium ions inside the cell, there's sodium ions outside the cell, and the cell has a slight negative voltage. At the business end of the cell, there's a little molecule sitting there. This is called the neurotransmitter, and the job of the neurotransmitter is to jump across the synapse to trigger the next nerve cell in the line. Okay, the signal comes down the line, the neuron becomes excited, and passageways in the cell wall open up, and these passageways are sodium channels. They will allow sodium to flow into the cell. So sodium flows from outside the cell into the cell, which means that the voltage becomes positive. So the neuron is excited, it's now at plus 30 millivolts, and the neurotransmitter is released. Now this neurotransmitter is a little molecule called acetylcholine. It's released, it crosses the synapse, and when it gets to the nerve cell on the other side, it then excites that one, and the message continues down the line. So the nerve cell that we're looking at now has to get back to its original state. Passageways in the cell wall open. These are potassium channels, and potassium is released. The final thing is that ion pumps redistribute the sodium and potassium. So the potassium goes back in the cell, the sodium comes out, and we're back where we started. We're back at the original state. Now, the neurotransmitter has done its job, so at some point it either has to go back to where it started or it has to be removed. And it's removed by being destroyed by a particular enzyme called acetylcholine esterase. And this whole process takes 2 milliseconds. Very remarkable piece of chemistry. But, remarkable piece of chemistry, what happens when we interfere with it? And sarin interferes at the neurotransmitter stage. Suppose we have excess of the neurotransmitter present. What will happen? Well, it means we get continued nerve stimulation. Even though there is no signal coming down from the line from the brain, the nerve is still stimulated, and that means that the muscles at the end of the nerve are still activating. This leads to twitching, it leads to convulsions, it leads to paralysis and death. It often starts with blindness due to the effect on the eye muscles and the eye nerves. Now, under what circumstances would we have excess of the neurotransmitter present? Well, the concentration of the neurotransmitter is regulated by this enzyme called acetylcholine esterase, which converts the acetylcholine into inactive choline. What sarin does is block the action of that enzyme so that the excess acetylcholine cannot be destroyed and therefore will be present in excess. Well, I don't know if you've seen this movie. It's called The Rock. It was made a few years ago, and it stars as the heroes Sean Connery and Nicolas Cage, with Ed Harris as the villain. Well, in this movie, some renegade US soldiers steal some sarin-containing chemical weapons and take over the island of Alcatraz in San Francisco Bay and threaten to fire these weapons at San Francisco. So Nicolas Cage and Sean Connery are sent into Alcatraz to defeat this dastardly scheme. In a scene towards the end of the movie, Nicolas Cage is exposed to sarin when one of these things go off, and very dramatically he pulls out this syringe he's been given earlier on, and he stabs himself in the chest with this syringe. And then everything's fine, and the bad guys are dealt with, and Nicolas Cage gets the girl, and there's a happy ending. Now, what was in the syringe? The answer is a naturally occurring chemical called atropine. And atropine is the antidote to sarin. The reason it's the antidote to sarin is because it has the opposite effect. Whereas sarin inhibits the action of acetylcholine esterase, the enzyme, atropine inhibits the action of acetylcholine. So if you have excess acetylcholine present, atropine will prevent it from acting. So the atropine does the opposite to the sarin. So provided the doses are about balanced, then it's going to work as an antidote. On the other hand, if you take atropine just as atropine and not as an antidote, then it will be toxic because it's going to inhibit this action of your neurotransmitter. And as you can see there is an LD50 for atropine in rats by oral administration. Now, atropine, as I said, is a naturally occurring compound, and it comes from the plant Atropa belladonna. So it gets its name from the Atropa part, but what about the belladonna? Well, belladonna is Italian for beautiful lady. And one of the effects of atropine is that if atropine is placed in the eye, then the pupil dilates, so the pupil becomes bigger, and many people consider this to be beautiful, hence belladonna, beautiful lady. And in fact, one of the uses of atropine is in optometry, because if you put it in someone's eye and you dilate the pupil to make it bigger, then it's easier for the ophthalmologist to see inside. Provided it's only on the surface of your eye, it's not going to do you any harm at all. But of course, if it's ingested, then as we know, it's toxic. I mentioned at the beginning of this lecture that one of the reasons that poisoning is less common nowadays than in the old days is because it's much more difficult to get hold of these very, very poisonous substances. However, one group of people who can get hold of these substances relatively easily are chemistry professors. And this case here involves a professor of biochemistry, Paul Agata, who used to be at Napier University in Edinburgh, Scotland. And he was convicted of poisoning his wife with atropine, which he had obtained ostensibly for research purposes. So, how did Agata do it? Well, he put atropine in his wife's gin and tonic. Now, if a wife is murdered, then of course one of the first suspects is going to be the husband. And Agata knew this, so he laid a false trail to try and mislead any investigators. He went to a local supermarket and took some of the bottles of tonic water and spiked them with atropine, and then returned them to the supermarket. His idea was, by having random people around the town having mild atropine poisoning, people would think this is some kind of serial killer, or maybe someone with a grudge against the supermarket or the drink manufacturer, rather than a husband trying to get rid of his wife. Unfortunately for him, his scheme unraveled, and that is because the amount of atropine he put in the tonic bottles was less than the amount of atropine that he put in his wife's drink. These things, of course, are very easy to measure using a technique such as HPLC. So it was very clear to the police that it was actually a husband-wife case rather than a mass poisoner. Well, fortunately, his wife got medical treatment, she survived, and Agata was convicted only of attempted murder, and he served 7 years in prison. Interestingly, after his release from prison, he started to work for the University of Manchester, and they asked him to teach a course on medical ethics. Georgi Markov was a Bulgarian writer, but he had become dissatisfied with the communist regime in Bulgaria. And in 1971, he had defected to Britain, and he'd started working for the BBC World Service, broadcasting to Bulgaria in Bulgarian, saying very unpleasant things about the then Bulgarian regime and the then communist Bulgarian president. These things did not make him popular back in Sofia. Now, one day in September 1979, he was on his way to work, and he was standing on Waterloo Bridge when he felt a sharp pain in one of his legs. And he'd been poked in the leg by an umbrella held by the man standing next to him. This man mumbled an apology and then disappeared. Well, Markov went on to work, but he started to feel unwell. The next day, he was admitted to hospital, and on the following Monday, he died. Well, at the autopsy, the puncture wound from this poke in the leg was found, and the tissue from that part of the leg was sent to Porton Down, the chemical weapons research establishment. And in the tissue, there was a very, very tiny metallic sphere. SEM-EDX analysis showed that its composition was very unusual. It was an alloy, 90% platinum, the rest was iridium, not the kind of alloy you'd come across in normal life. This sphere was hollow, there was a tiny hollow space inside, and they estimated this was big enough for about 2 milligrams of poison, though there was no detectable poison inside it anymore. It was deduced that the poison most likely to have been used inside that metal sphere was a complex polypeptide called ricin, and this can be isolated from the castor oil plant. Rather scarily, the castor oil plant is very, very common. It's quite an attractive plant, and many people might find it growing in their garden. The umbrella was, of course, not a real umbrella. It was, in fact, a pellet gun disguised as an umbrella and probably made by the KGB. This technique had, in fact, been used the previous year on another Bulgarian dissident called Kostov. The difference was that whereas Markov died from the ricin poisoning, Kostov had survived, and it's believed this is simply because of the way they were stabbed. The pellet injected into Markov came very close to a blood vessel, and therefore the ricin was absorbed very fast, reaching a high and lethal concentration. The pellet injected into Kostov probably went into muscle tissue, and therefore there was a very slow absorbance of the ricin into the bloodstream. Well, was Markov really murdered by the Bulgarian secret services? It seems very likely that this was the case, though many of the records of the Bulgarian secret service disappeared with the fall of the communist regime, and many important people in that regime committed suicide, so they can never tell us the truth. Our final poisoning case in this lecture is a little bit different from all the others. It concerns the Russian Alexander Litvinenko, who died of poisoning in 2006. So if we look back at Litvinenko's career, he'd started out as an officer in the KGB and stayed on when the KGB converted into the FSD. By 1998, he had become a serious critic of the Russian government, and a couple of years later he sought asylum in London, where he continued to be a critic of the Russian government. After 6 years in London, he became seriously ill and he died in hospital. You can see from the picture that one of the symptoms of his illness is hair loss. So of course it was thought that probably this was thallium poisoning. But when he was analyzed, for instance, analysis of his urine, there was no thallium detected. And it turned out that he was being poisoned in a very, very unusual way, for which there was no known precedent. And that is, he was being poisoned with polonium-210. Now, polonium is a radioactive element. All forms of polonium are radioactive. Polonium only occurs naturally in very trace amounts. So polonium is actually manufactured in nuclear reactors. And one of the few places that manufactures polonium-210 is in Russia. Now, polonium-210 is radioactive. The atoms of polonium-210 decay to become lead-206, and in the process of decay, they emit an alpha particle. That is, a radioactive particle is spat out of the atomic nucleus. Now, alpha particles are not really that dangerous. They will only travel for a few centimeters in air. they will only travel for a few micrometers through the skin. So polonium-210 itself is not very dangerous, provided it's contained. But if it is ingested, it's very, very dangerous indeed. Because if polonium-210 is ingested, there is no barrier between these unstable radioactive atoms and your biochemical molecules. So when these atoms decay and they give out that alpha particle will smash into important molecules in your body, your enzymes, your molecular structures, your DNA. So it's not like the other poisoning cases that we've talked about before. This is radioactive atoms attacking your molecular structure. So nothing could be done, and Alexander Litvinenko died in hospital of radiation poisoning. The thing about radiation is that it's very characteristic. The energy of these alpha particles given out by polonium-210 is highly characteristic. Other radioactive atoms that give out alpha particles will give out alpha particles with different energies. So it's very easy to trace the polonium-210 and to confirm that it is polonium-210. So as the police followed the trail of Alexander Litvinenko around London, they were able to find more than 30 locations where there's polonium-210, including the places where Litvinenko had lunch and had tea. And it's believed that the polonium was put into his food or drink at one of these occasions. They were also able to trace polonium-210 on 2 British Airways planes. In fact, they could track it to the particular seat on the plane, and these planes were flying on the London to Moscow route. So the Metropolitan Police have a suspect in mind, someone who they would like to have help them with their inquiries. But forensic science can only do too much. It's now part of international politics. It's a question of whether the Russians will arrange for this person to ever come to London for questioning. Well, this concludes our lecture on toxicology, and we've covered a lot of ground. We've talked about all sorts of different poisons, from plant poisons to carbon monoxide to inorganic poisons. We've seen some of the different modes of actions that these poisons can have, and how important it is to consider the route of administration for a particular poison. We've seen the use of the LD50 value to measure how strong a poison is. We've seen how important it is that you keep your liver in good health to protect you from xenobiotic molecules. We had a quick look at alcohol, the most common poison. We talked about Paracelsus, and then we've seen the action of some specific poisons, such as arsenic, thallium, sarin, and atropine.